Okay, let us begin with type 1, part A. As you have noticed, we have divided the type 1 into two different sections, like type 1, part A and type 1, part B. Both parts have the same mantra, have the same idea, are solved using the same technique, but type 1 part B is a little bit different. So we included this one first because we thought that it was like nice for you to have like solving these easy equations first and then make it a little bit more complicated, but it's just a little bit more complicated. It's almost the same thing. So the mantra that you need to have in your head when solving type 1 equations is that you want to have the same base. You want everything in the equation to have the same base. So for example, if we go to question number 23, in question number 23, I have 243 to the power of x minus 2 equals to 9 to the power of negative 3x. By saying that I want to have the same base, I mean that I want to rewrite these numbers, the 243 and 9, so that they are the same numbers. Now remember that the big number in the exponents is the base, so I want this and this to be the same number. Oh, and you very quickly notice that 9 is the same as 3 squared. If you write the powers of 3, so 3 to the power of 0 is 1, 3 to the power of 1 is 3, 3 to the power of 2 is 9, 3 to the power of 3 is 27. And I have a feeling that this one, the 243, would be in this list. If I just persevere for a couple of more numbers, 3 to the power of 5 is 233. 243. So by knowing that 3 squared is 9 and 243 is 3 to the power of 5, I can rewrite this equation. So instead of writing, this is the original equation, and so what I am doing from here to here is that I am changing the number. Instead of writing 243, I am writing now 3 to the power of 5. And instead of writing 9, I am writing 3 squared. So now I almost have I have the same base, no? And there are some operations that I can do. By the multiplication rule of exponents, I only do the exponent times the exponent, so it is 5 times x minus 2 and 2 times negative 3x. And that is what I have here, and that is what I have here. Now I have the same base, and because I have the same base, I can cancel out the bases, no? Because of the injectivity of the exponents, no? 3 to the power of something equals to 3 to the power of something, so these two things should be the same. And this is like a 7th grade equation, no? I just like multiply the 5, multiply the 2, add 10, subtract, add 5, add 6x, divide by 11, and this is my solution. So the whole idea in this first type of problems is that you want to have the same base. Like I look at these two numbers, and the 9 is suggesting me, the 9 is like whispering me, maybe you need to use 3 as a base. And if I go through the powers of 3, I can find 243. A little hint that I want to give for, I don't know if it is the next one or I don't know, this one. So again, I see a 36, and because I know my perfect squares very well, I know that 6 squared equals to 36. So I want to find the 1 over 216 as a power of 6. I persevere and I see that 6 to the power of 3 is 216. But this is a fraction and this is a whole number. So remember that to write this fraction as a power of 6, it is a negative power of 6. Great. Oh my god, for me it's super weird doing this because I never receive like the feedback or like the yes, Mr. Cachoa, move on. I hope that it was clear. So type 1 part B is the same thing. I want to have the same base. That is my mantra. I want to make the equation so that every exponent has the same base. What is the difference with this equation and the one that we just saw before? I have an extra step. I have an extra operation. And this extra operation is in the same base as 4, no? Because this, I am here, now I am multiplying by 16. There are two ways in which I can solve this problem. in which I have an extra operation in the same base. So an idea is to get rid of the operation. So very naturally, if I am multiplying by 16, I divide by 16. So this 16, I move it to the other side dividing. 16 over 16 is 1. The 1, I can write it as, you know, this appears in the powers of 4 as 4 to the 0. I have the same base, so I can just cancel the 4's, so 3r equals to 0. I think that is a very nice way of doing this. There is another. So because the 16 is in the same base, so my equation is 16 4 to the power of 3r equals to 16. Oh, because this is my equation, and my equation, like, I can write it all in the same base. I can do, well, 16 is 4 squared. So it is 16 4 squared times 4 to the power of 3 equals 4 squared. And to cancel the bases, I need to have only one exponent on each side. You cannot say, oh, Mr. Cacho, I only have 4s, let me get rid of those 4s. No. I need to have only one exponent on each side, like this expression. So what did I do to this equation to get this equation? I applied the exponent rule of adding exponents, no? Because this is the same base, I can add the exponent, so it is 2 plus 3r. Now, if you look at this expression, I have 4 to the power of something equals 4 to the power of something. So now I can cancel the 4's. I cannot do this here. No, I need to have the same base and only one exponent. Then that is again a 7th grade equation, 2 plus 3r equals 2. Subtract 2 on both sides, divide by 3, r equals 0. Very nice. Very nice. Okay, type 2. So in type 2, I want you to notice what is the difference between type 2 and type 1. Here I have 11, 5, and 17. So 11, 5, and 17 are 3 prime numbers. I cannot write 11 as a power of 5 or 17 as a power of 5, nor any other combination. In this one, very sadly, I cannot use the same base. That is sad. So my mantra, the way of solving a type 2 equation, an exponential equation that do not use the same base, is to use logarithms. That is why we created logarithms. That is why logarithms are here, to solve this type of equations. So the idea in this problem is that I isolate the exponent. The exponent is the guy with an exponent. Isolate it, leave it alone in one side of the equation, and then transform it as a logarithm. So my mantra, when I cannot make every number into the same base, is isolate the exponent and transform to logarithm. So how do I leave this exponent alone? Very clearly, I just need to subtract the 5. So I have my exponential equation. I subtract the 5. Very nice. And then, oh my God, this is the definition of a logarithm. So I have one student who told me, like, oh, Mr. Cacho, but I can still do not understand what a logarithm is. So a logarithm is the inverse operation of an exponent, and you understand exponents very well. So a logarithm, in a sense, is the opposite of doing an exponent. If you write an exponent as like this, the logarithm is written like this. This formula. This is a very important formula. Crazy important. It won't be given in the exam. Okay, if there is a poster in the room with the formula, I will tear it apart and destroy it, because you need to know it. You need to know what a logarithm is. A logarithm is transforming or rearranging the numbers in an exponent. So a is called the base, x is called the exponent, and y is called the argument. Okay, sorry. So now that I have this equation, that it's an exponential equation, a is 11, x is negative 2b, and y is 12. So now I write it as log base 11 of the argument 12 equals to negative 2b. The logarithm, if you see, it pulls down the exponents, no, into equations. And now this is a number. This is a number that you can find in a calculator, and I won't ask you how to find this number. I don't care if you know how to find this number. This is a decimal. Finding the exact value of this was another part of the test, no, the beginning. So what I want you to do is to leave b alone, no, isolate b. So if you have already written this, don't be afraid. This is just a number. So I divide by -2, and this is the value of b, and you leave it like that. That is a perfect answer. That is a beautiful answer. It is a number divided by -2. So the idea is that you need to isolate the exponent and then transform using the definition. Okay, very nice. Very nice. Type 3. So in type 3, this is different to the exponential equations. No, if, the equations that we have been doing are exponential equations, not logarithmic equations. In this case, I have a logarithm instead of an exponent. So something that many people said is that, oh, Mr. Cachoa, in the packet, in the handout, there is no, this parenthesis is not there. So I am sorry. In the exam, I'm gonna ensure that the parenthesis of what is inside of a log is clear. But there is a parenthesis here. No, I just wanted to say that. So what is the difference between this equation and the ones that we have seen? That this it is like type 2, but instead of an exponential, it's a logarithm. So my mantra, as it was in type 2, my mantra is that I need to isolate the logarithm and then transform it to an exponential. So if I have this equation for log base 7 of -n equals to -8, so to isolate it, the operation that it's outside of the logarithm is the multiplying by 4. So the opposite of multiplying by 4 is dividing by 4. So -8 divided by 4, it's -2. Now that I have it written as a logarithm, I want to write it as an exponent. So my base is 7. 7 to the power of the exponent -2 equals to the argument -n. Now, please don't be afraid. Please don't be afraid. Now, I just move the negative to the other side, you know, by dividing by -1 on both sides. And then I flip because I like having my variables in the left, no? To the left. So this would be my answer. If you want to write it as a fraction, as -1/49, that is also okay, very good, very good. But like, this is a good enough answer for me. No, that is a number, and we shouldn't be afraid of numbers written like this. So again, isolate the logarithm, transform into an exponential. So type 3 is easy as type 2 is easy, no? Type 4 is like a very tricky type of equation. In type 4, what is the difference? What makes this type of equation different from the other ones? Well, that this one has a logarithm on both sides, and there are no operations outside, no? So logarithm on both sides and no operation outside. And as we did in type 1, when we had the same base on both sides, we tear it apart. So we can cancel the log on both sides. And that is my mantra, cancel both logs. And you need to check for extraneous solution in every logarithmic equation. But in the previous equations, I've never had an extraneous solutions. Extraneous solutions may appear from now on. So in type 4, a very easy cancel the logs and check for extraneous solutions. I will remind you what extraneous solutions are in this context. So let us solve it. I have my equation. I cancel the logs. Oh, that is very easy. That is very nice. That is a quadratic. A quadratic that you have solved during Algebra 1. A quadratic that we solved at the beginning of the year, so a long, long time ago. So when I want to solve a quadratic, because I have an exponent of 2, and I have a linear exponent, I make it equal to 0. you're experts doing this, then you can do quadratic formula, you can graph a parabola if you're a freak, or you can factor, no, if you're a very classy person. So I need to find two numbers that multiply to 50 and add to 15. Very clearly, the two numbers that multiply to 50 and add to 15, remember, multiply to the third, add to the one in the middle, are 10 and 5. Instead of writing 15, I write 10 plus 5. You know, this is the same equation as this one, but instead of 15, it's 10 plus 5. I factor. I take a common factor here, that is p. I take a common factor here, that is 5. I write as two parentheses, boom, boom, boom. P equals negative 5, p equals negative 10. Easy peasy. Now we need to check for extraneous solutions. So, in the context of logarithms, the argument, the thing inside of the log, it should be positive. So I need to check that when I plug in these numbers into the things inside of the log, these expressions are positive. So I'm gonna do it first with negative 5 and then with negative 10. So negative 5. I plug in negative 5 inside of p squared plus 53, so negative 5 squared plus 53, that is 25 plus 53, and that is positive. Then negative 5 inside of negative 15 times p minus 3. Negative 15 times 5 is, times negative 5 is something positive. I don't know what it is, maybe 75. 75 minus 3, okay, that is positive. So this is not an extraneous solution, this is a solution. No, this is a solution. Very nice, very nice. And now we need to check the other number. The other number is negative 10, and the negative 10, so again negative 10, p squared plus 53, o sea, negative 10 squared plus 53, that is positive, very clearly positive. Negative 15 times negative 10, 150 minus 3, that is clearly positive. So there are no extraneous solutions in type 4, in this particular equation. So if I were, like, whenever you're solving in your adult life a logarithmic equation, you will need to check for extraneous solutions. But I won't be like including extraneous solutions in every type of the equation, because these are very easy. No, these are very easy. These are quadratics that have like a little extra step. Okay. So now we're almost done. Type 5. So look at equations in type 5. What makes different equations in type 5 from the other ones that we have solved? So these are logarithmic equations. I don't have logarithms in both sides, and I have operations outside of the logs. No, like I have this logarithm, and I have something outside of the logarithm. No, it can be an addition or a subtraction. So I have operations outside of the logarithms. And in the very particular case that we're doing today, that we're doing for this class, I have logs in only one side. No, I don't have logs in this side. The mantra of type 5 is using one of the important properties of logarithms. I'm going to combine these logs using the properties of logarithms, and then I'm going to transform them into exponents. Okay, so how do I combine them? These are two formulas, two very important formulas. When adding logarithms, the logarithms multiply. When subtracting logarithms, the arguments divide. And that is the same as with exponents. Well, it is the opposite as with exponents. No, if I have like a to the power of n times a to the power of m, the solution is a to the power of n plus m. So in exponents, multiplying exponents makes that the exponents add. Here, adding logarithms makes that the arguments multiply. No, so it is the opposite. And as well as with subtraction and division, if I subtract logs, the arguments divide. For type 5, I'm going to do both problems 43 and problems 44. So problem 40, problem 44, 43. So I have my equation here. log base 4 of 5 plus log base 4 of x squared minus 8. So because they are adding, I multiply the two arguments, this times this. I distribute inside 5x squared minus 40. And look, this is a type 3 equation, no? Where I have a logarithm equals to a number. So because the logarithm is already isolated, I just need to rewrite it as an exponent. So this is log base 4 of 5x squared minus 40 equals 1. So 4 to the power of 1 equals to 5x squared minus 40. And I've solved this equation, it's a quadratic, but I only have a quadratic term. I don't have a linear term. So this is very easy to solve because I can add 40 on the other side. I flipped it, sorry. I am a freak. I like having my variables in the left hand side of my equation. And then I can divide by 5, and that is x squared equals to 44. I didn't need to use factoring or quadratic formula, no? And then my solution is the square root, the plus minus square root of 44 over 5. Please convince yourself that none of the two solutions are extraneous. So the idea, look, I had the two logarithms, they were being added, I turned the addition into a multiplication, then I turned the logarithm into an exponent, and then I solved. Let us look at this one. I have log base 6 of 5 minus log base 6 of 3x minus 3x equals to 2. Because this is a subtraction, the subtraction turns into a division. This is 5 over oh my god. Catsup. 5 over minus 3x equals to 2. Híjoles, this is a very nice moment. I'm not gonna edit it. That is 5 over minus 3x equals to 2, no? Because this is 5, this is minus 3x. So a question that was asked to me is like, which one goes in the numerator and which one goes in the denominator? The one that goes in the numerator is this one. This one goes in the numerator. And this one goes in the denominator. The first one goes in the numerator and the second one goes in the denominator. So over and under, over and under. Then I have logarithm of a rational expression. The logarithm is by itself, so I can write it as an exponent, no? So that is 6 to the power of 2 equals to the thing inside. So that is 6 squared equals to 5 over negative 3x. And to solve for x, like I move the x, like I multiply by minus 3x, 36 times minus 3x, that is negative 108x, and then I divide by negative 108, and that is 5 over negative 108. Okay. So basically you have a subtraction, the subtraction turns into a division, the log turns into an exponent, and you solve. Okay, now one more equation. This is the hardest type of equation, no? Type 6. In type 6, we have this. So what do you see? What makes this equation different? This equation, again, is an equation with exponents, and I have two different bases. No, this is an exponent base 2 and an exponent base 5. So I have different bases, and there are no operations outside of the exponents. So here, very sadly, have you seen how I have thought of like these mantras to solve each of the different type of equations? Here, there is not a single simple mantra. So the way that I would like to say it, my mantra here would be like, okay, so you would do log base 10 on both sides. You use the multiplication law of logarithms. Then you do x's on one side and no x's on the other side. Then you factor to isolate x. I know. Up to now it's a horrible mantra, but like this is the last step, because the last thing that I wrote is don't worry, be happy, which is a very nice mantra for your life. But these 4 steps are the things that you need to remember, no? Log on both sides, multiplication law, x's on one side, no x's on the other side, factor to isolate x, and then don't worry, be happy. Okay, let us try to do it. What is a multiplication law? So in logarithms, addition turns into multiplication, subtraction turns into division, and exponents, if I have an exponent inside of a logarithm, this exponent goes down. So exponents inside of logarithms, if the term is alone, if this is a single term, this exponent can go down. And I am saying that it's a single term because, for example, in this problem, in the previous problem, 43, I have log base 4 of x squared minus 8. And you may be saying, oh, Mr. Cachoa, why don't we take this 2 down? Well, because this is not a single term. The x squared is not alone. If I have logarithm base 4 of x squared, then that is the same as 2 log base 4 of x. But I cannot do the multiplication law if I am not alone inside of the logarithm. So this is the law of multiplication. Exponents inside of the logarithm drop as factors in front. Using this fact, we can solve this equation. So I have my equation. I use log on both sides, and log without a number is the same as log base 10, no? So you don't have to write it. If you write it, I will be upset. So log on both sides, apply log on both sides. That was the first part of the mantra. Then use the multiplication law. So this exponent will go down as a factor, and this exponent will go down as a factor. So look, I have exponent in front of log base 2. The log 2, of log base 10 of 2. O sea, it is log 2. X minus 3 in front of log base 5. Of log 5. Log base 10 of 5. Okay. Up to now, nothing horrible. The next step, I have found that some people find it complicated. So what am I doing to go from here to here? So log 2, this is a number. This is a decimal, right? It's a number. Log 5 is a number. So what I do is that I multiply this number times each of the things inside of the parentheses. So it is log 2 times x, that is x log 2, log 2 times 2, that is 2 log 2. This again is a number, so I just multiply by x and by 3. That is log 5 times x log 5, and log 5 times negative 3 log 5. So after applying the multiplication rule, putting the exponents down, I distribute this number called log 2 on each of the terms on both sides, no? Great. I have a beautiful equation. This is, and I just want you to really think about it. This is a linear equation. This is a line, and that is very nice. Even though that it looks intimidating, no? But log 2, log 5, those are numbers, no? This is one of those equations that you solved in 7th grade, but written in a scary way. But you're not scared because you're grown-ups now. So what am I doing in the next step? So my mantra said, okay, x on one side, no x on the other side. Look at this term. This term has an x in front. So I'm gonna keep it on my left-hand side. This does not have an x, so I'm gonna move it to the other side. This one has an x, so I'm gonna move it to the other side. And this one, ay, perdónenme, niños. And this one, it's because you know something, doing this video takes a lot of time. I could edit this, I could erase it, I could stop, but no, I just really want to do it and send it to you. So it's okay. You just met my cat. Okay. The terms that have an x, go to the left-hand side. So this one stays here. This one, I move it to the other side with minus, no? So I subtract x log 5 on both sides. And this one, because it doesn't have an x, I move it to the other side, I subtract negative 2 log 2 on both sides, so it erases from here and it becomes negative in this side. Very nice. The last part of my, the second to last part of my procedure. So look, here I have x log 2, x log 5. So x is multiplying this number and x is multiplying this number. What I am doing from this to this is that I am factoring the x. I am pulling the x, no, from these two terms. So this becomes x times log 2 minus log 5. So here I am just factoring. And you may be saying like, oh, Mr. Kerchow, why are you doing that? Trust me for a second. Because now this is x alone multiplying by this number equals to this number. So to isolate x, I just need to divide by this number. So this number goes to the other side, dividing. And that is how you solve type 6 equations.